And welcome to my YouTube channel. So here today we are going to be looking at the concept of ideal gas laws. So an ideal gas is simply a gas that obeys the gas laws. So now in real life, no gas is an ideal gas. So what are some of the assumptions that are made under the ideal gas law? So under this one, the first assumption is that gases are very small, such that their volume is negligible as compared to the volume of their content. In other words, what we mean to say is that gases have got negligible volume. So now, this assumption is that if, let's say, you have one container like that, when you're looking at a gas like that, it is very small as compared to the volume of the whole container. Due to this, you will find that gases tend to be having negligible volume in comparison to the container that they are stored in. So that is the first assumption. The second assumption is that gases do not interact. So what this means is that they do not have attractive or repulsive forces between them. So that is what we talk about. They do not repel or attract each other. So now let's look at questions which we are going to attempt. So at the end of this video, you should be able to answer all these questions, which are examinable questions. So let us begin. So before we answer questions, let's look at the requirements. So under the requirements of the ideal gas behavior, we have very high temperature. That's the requirements number one. Requirements number two is that very low pressure. Now, when the temperature is very high, it means to say, let's say if we have two gas particles like that, that means to say the gas will not have enough time to interact with each other. So that is why this is very, very important. The temperature must be high so that they do not have chances to interact with each other, to attract each other, or to repel, because they are moving so fast like that. So that is what we mean by the ideal gas law. The temperature has to be very high and it has to exist under very low pressure. Then the formula for the ideal gas equation is our PV is equal to our nRT, like that. Then what we have is, where this one, we have our pressure, we have our volume, we have the number of moles, we have the R, we have our T, like that. Now the condition is that for when you take, this is the universal gas constant. So this is what we have. We have our volume like that. We also have the R is the universal gas constant. We also have the number of moles like that. We have the pressure like that, and we have the temperature. So what are the requirements? So R might assume two values, which are, if you are looking at R, when R is equal to 0.08206, the units are liters, atmospheres per mole, times the Kelvin temperature. So that means to say, if you are using the universal gas constant of 0.08206, under this one, you must know to say your volume must be in liters. That's where the L is. Your pressure has to be in atmospheres. Then also we have the moles. You must have moles, and the temperature has to be in kelvins, like that, degrees kelvins, like that. The other gas, the universal gas constant is our 8.314 joules per mole per Kelvin, like that. So now what this means is that for this one, what you need is your volume has to be in meter cubed. Then also we should have the pressure has to be in pascals. So you should make the conversions from that to that. But for this video, we are going to be using this ideal gas. So you can use this equation by just converting to liter, atmosphere, the mole, and that. So now let's look at our question now. So the question says, calculate the volume occupied by 0.85 moles of nitrogen gas at a pressure of 1.37 atmospheres and a temperature of 315 kelvins. So you're going to use your PV is equal to your nRT like that. So you can make the V, what are we looking for? The volume. You can make the volume the subject of the formula by dividing pressure on both sides, so that the volume becomes equal to nRT over the pressure. So the volume is equal to our number of moles. We have 0.845 moles times the gas constant. We have, if we have the moles, then we have the pressure in ATM, and the temperature in kelvins. We are going to use the universal gas constant of 0.08206 like that. Then we have times the temperature is 315 kelvins like that. 315 kelvins over the pressure. So the pressure we have been provided with is equal to, we have a 1.37 atmospheres like that. So the volume, the result of the volume will be in liters, which is equal to, we are going to multiply on top. We have 0.845 times 0.845 times 0.08206 times 315. We are going to get a value of a 21.842. We divide by 1.37 atm. We are going to get our volume will be equal to, we have 1.37. This is going to give us a value of 15.94 liters like that. So this is our volume. So our volume is equal to 15.94 liters like that. Let's move on to our next problem. So we have a balloon contains 8.8 moles of helium at a pressure of 0.992 atmospheres and a temperature of 25 degrees Celsius at ground level. What is the volume of the balloon under these conditions? So we are going to have, so as long as you have the number of moles, you have the pressure, you have the temperature, just think of the ideal gas law. So knowing that the ideal gas law is PV is equal to our nRT like that, we need to check, is the temperature in kelvins? So to convert the temperature to kelvins, we are going to say temperature in kelvins. So remember how we convert, we are going to say temperature in degrees Celsius plus 273.15. Now, what we are going to have is that the temperature in degrees Celsius is equal to 25 degrees plus we have the 273.15 like that. When we add these, we are going to get, so we have a 25 degrees Celsius plus that. We are going to have, let's just avoid the units. Yeah, so for the sake of this topic, we are just avoiding those units. So we are going to have, anyways, we can always do this degrees Celsius, then say 1 Kelvin over 1 degree Celsius, but you can just avoid them depending on how difficult your lecture is. So you're going to add your 25 plus your 273.15. This is going to give us a value of 298.15 kelvins like that. So you have the temperature in kelvins, your volume is unknown, your pressure is in atmospheres, so you can use now. So we have the PV is equal to our nRT. So we are going to have the volume, so we are going to divide over the pressure, then we are going to have our volume is equal to our number of moles, according to this is 8.8 like that. We have times the universal gas constant 0.08206. Then we have times our temperature, we have found it to be 298.15 kelvins like that. Then over, we have our pressure, which is equal to, so our pressure is equivalent to 0.992 like that. So volume is equal to, let's multiply on top 8.8. So we have 8.8 times 0.08206 times 298.15. This is going to give us a value of 215.302. Then we are going to divide over our 0.992 like that. So our volume should be equal to, we have 215.302 divided by 0.992. This is going to give us a value of 217.04 like that. Then we have the units, liters like that. Let's move on to our next problem. So before we answer the remaining questions, let's understand how we move from PV is equal to nRT to finding the density. So now we know that the number of moles is equal to mass over the molar mass. So we are going to have our PV should be equal to the number of moles is the same as mass over our molar mass. Then we have R, then we have our T like that. Then what we are going to do is that we are going to cross multiply. Then we have our PV, M times this, we are going to have MM should be equal to this mass times 1. 1 doesn't change anything, so it will return to M times R times our T. Then we know that density is equal to, we have our mass over the volume. So we are going to divide over volume over the volume. So whether you write like this, whether you just write like this, it is still the same, because if you have a number such as 2, let's say you have 2 times 4 over, let's say 2. If you put it like this, it will be over 2. 2 divided by 2 is 1. 1 times 4 is 4. Even if someone was to write like this number divided by our 2 is equal to 2 times 4 will give you 8 over 2, which is still equal to 4. So regardless of how you write that one, it's still the same. So we are going to write like that. Then this and this cancels. Then we have P, then we have M should be equal to mass over volume is equal to the density. Then we have R times our T like that. So this is how we move. Now to help you remember this, this is the simple way of remembering it. We have the Mr. P is equal to Dr. T like that. So Mr. small letter meaning the molar mass. Mr. P is equal to Dr. T. And you know to say the words doctor has got a T. So you can use Dr. T is equal to Mr. P like that. So this is a simple way of remembering. You don't have to be deriving each and every time. Let's answer a question. So let's say we have this question. Calculates the density of nitrogen gas at 125 degrees Celsius and the pressure of 755. So we have Dr. T is equal to Mr. P like that. So knowing this, we are going to convert the pressures to be in atmospheres, the temperature in kelvins. So we have the temperature in kelvins is equal to the temperature in degrees Celsius plus 273 degrees. So using the alphabet is really helpful, because you know that for you to move from C to K, you have to add a certain value. That way it can help you. So we have the temperature in degrees Celsius here is 125 degrees plus 273.15. So when we do the calculation, we are going to end up with 125 plus 273.15. This is going to give you a 398.15. So this is the temperature in kelvins like that. Then when we do that, we are going to now convert the pressure in atmospheres. So from this value, so you can watch the video for unit conversion of temperature. So we have, if we have 755 millimeters, as long as you have millimeters of mercury, just divide this number. So using the Chandling conversion, you can say that this shall be equal to, we have 1 atmosphere, put it on top. In 1 atmosphere, there is exactly 760 millimeters of mercury. So we are going to say that this one and this one goes, so we are remaining with the unit of atmospheres like that. then divide. So our 755 divided by 760, this will give you a value of 0.9934 atmospheres. So we have converted that. If you want, you can say that 1 atmosphere is equal to 760 millimeters of Hg. Then how about if you have 755 millimeters of Hg, you are going to have X. This will still give you the same answer. So we have found this value. So with these values, we can now be able to calculate the density. So knowing that the density should be equal to, we have our Dr. T is equal to our Mr. P, like that. So we are going to have, we divide by our RT, so the density is equal to the molar mass times pressure over the RT, like that. Then our density should be equal to our molar mass of what do we have? Nitrogen gas. So nitrogen gas, so we need to find the molar mass. Now don't just write nitrogen. Nitrogen gas is diatomic, meaning to say it exists like this, and 1 nitrogen is equal to we have a 14.01, but there are 2 of them, so we are going to multiply by 2 to get a 28.02, like that. So we are going to have 28.02 grams per mole. Sorry, this is the molar mass, not the density. Anyways, we have calculated that. That's our molar mass, like that. Then we multiply. What is our pressure? So our pressure is equivalent to we had a 0.9934 atm. We divide over our R, which is our 0.08206 times what is our temperature. So our temperature was found to be 398.15 degrees Kelvins, like that. So our density in this case shall be equal to, so when we do our calculation, we multiply on top, we are going to get a, so on top we have 27.835. We divide this value over our 0.08206 times 398.15. We are going to have our 32.673 there. Then when we divide, our density will be found to be, so 27.835 divided by 32.673. This is giving us a value of a 0.852. So density will be grams per liter. So a liter is a unit of liter. 1 liter is the same as 1 cubic decimeter, like that. So these are the units for density that we are going to be using for this topic, a grams per liter. Let's say we have this one. What is the molecular weight of a pure gaseous compound having a density of this? Temperature -35 degrees Celsius and 1020 torricelli. So we know that our Dr. T, provided with the density, Dr. T is equal to, we have the Mr. P, like that. So we are going to substitute. Now we must make sure that the pressure, so torricelli is a pressure unit, we have to convert this pressure into atmospheres. So we are going to use the same approach. Our 1020 torricelli, we multiply by 1 atmosphere on top. Then since the torricelli is up there, we have to put down here, we have to put its equivalence. 1 atmosphere is equal to 760 torricelli, like that. So you can watch the conversion of units. So when we divide, we have our 1020 divided by 760. This is going to give us a value of 1.34, like that. atm, like that. So 2 there, atm. So if this is what we have, then what else do we need to convert? So we have converted the pressure, and also the temperature has to be in kelvins. So temperature in degrees Kelvin is equal to temperature in degrees Celsius plus 273.15. So the temperature in degrees is equivalent to, we have a negative 35 degrees Celsius plus we have our 273. So we have 273.15 there. When we add these, we are going to get something like negative 35 plus 273.15. This is going to give us a value of 238.15, like that. So this is the temperature in kelvins. So using our Dr. T is equal to our Mr. P, like that. So our doctor, so what do we want? We want the calculates the molecular weight. So we are going to have where are we now? To make the molar mass the subject of a formula, we divide by P. So this Mr. is just to help you remember, but it's the molar mass. So we have our DRT over the pressure should be equal to, we have the molar mass, like that. So the density is 4.95, like that, grams per liter, times the universal gas constant 0.08206, times the temperature is equivalent to, we have a 238.15. Then we divide this by the pressure. So our pressure is equivalent to, what is our pressure? Our pressure 1020 torricelli is equivalent to, we found 1.342 atm. So I can even put the molar mass here, whether I put it there, I put it here, it's still the same. So now, for those of you that do not know this way of conversion, you can just say 1 atm is equal to 760 torricelli. How about if you have the 1020 torricelli? What is the equivalence? You don't know, you can still use this. So we are going to have our molar mass should be equal to, so molar mass is equal to, let's multiply everything on top. So when we do our 4.95 times our 0.08206 times our 238.15, we are going to get a value of 96.735. We divide this by 1.342. We are going to get a value of a 72.1, and the units of this is grams per mole. The molar mass is grams per mole, like that. So this is our outcome for that problem. Let's look at our next problem. We have a sample of gas has a mass of 0.311 grams. Its volume is 0.225 liters at a temperature of 55 degrees Celsius and the pressure of this. Find the molar mass. So if you haven't been given the density, you begin. Your PV is equal to nRT. So they want the molar mass provided with the mass there. Now, this is the sample of a gas. You don't know which gas this is, so you cannot find the number of moles. So what you're going to do is that you know that the number of moles is equal to mass over the molar mass. So you're going to say PV is equal to, where there is the number of moles, you're going to say mass over the molar mass times our R times our T, like that. Then we are going to have, what are we looking for? We are looking for the molar mass. So we have to make molar mass the subject of the formula. So we are going to first cross multiply molar mass times PV. We are going to have PV times the molar mass should be equal to 1 times M. It's M. This times 1 doesn't change anything. So this is what we have. Then we divide over PV over our PV, like that. So the molar mass is equivalent to our mass times R times T over our PV, like that. So the mass should be, molar mass should be equal to, what is our mass? So our mass is given as 0.311 grams times our R is equivalent to, we have a 0.08206, then we multiply times the temperature. So our temperature is 55 degrees Celsius, so we first have to convert that. So our temperature in kelvins should be equal to 55 degrees Celsius plus 273.15. So when we add this 55 plus 273.15, we are going to get a value of 328.15. Then we are going to have the temperature in degrees should be equal to 328.15, like that. So we are going to replace that value. Let me move this. So we have a 300 and so Kelvin, we have 328.15 degrees Kelvin over, we have over our molar mass over our PV. So our pressure, we have to take this value, just divide. So take this value, we could have converted in advance. So converting 886 millimeters of Hg, you just divide by 760. That is the same thing when we do 1 atmosphere over 760 millimeters of Hg. If you want, you can just write whatever is in atmosphere, divide by this value, then multiply by 1 atm. This is going to give you 886 divided by 760. This is going to give you 1.16 atmospheres, like that. 1.17, in fact, 1.17 atmospheres. So we are going to put it there. So where are we? Pressure is 1.17 atmospheres. Then we multiply by our V, our velocity, our volume is equal to, we have, so our volume is equivalent to 0.225 liters, like that. So our molar mass should be equal to, we have our 0.311 times 0.08206 times our 328.15. So this is equivalent to, we have 8.375, like that. This value, we divide it by our 1.17 times 0.225. This is going to give us a value of 0.26325. Then we are going to get a value of, if we divide our 8.375 divided by our 0.2, that this is going to give us a 31.81. So we have the grams per mole, like that. So this is the molar mass. So due to rounding off, it is the reason why maybe it was supposed to be even for oxygen, which is a 32, which is close enough. But so we have this value that we have found as our molar mass. Let's move on to our next problem. So just to help someone, let's say we have a mole of a gas at 450 kelvins, has a density of 1.41 grams per cubic decimeter. So this is the same as cubic per liter. So dm to the power 3 is the same as cubic per liter at 2 atmospheres. What is the density of the gas at STP? So you must know one thing. STP means the pressure is equivalent to 1 atmosphere, and also the temperature. The temperature for STP, which is standard temperature and pressure temperature, is equivalent to 0 degrees, which when converted is equivalent to 273.15 kelvins, like that. If it was RTP, room temperature and pressure, the temperature is equal to 25 degrees Celsius, which can be converted into that other means. So now what we are going to have is that for this one, for that one where we have our Dr. Dr. P or Dr. T, sorry, Dr. T is equal to Mr. P. This one shows when the density is not changing, but when it's changing, use this formula. So now we know to say let's say at a school there is a pure class and there is also a TD class. You will find that the pure class is more higher than the TD class. So it is more respected. So you can say pure class over the TD class should be equal to pure class over the TD class, to help you remember. So P1, T1, D1, P2, T2, D2, like that. Then what are we required to find? We are required to determine the density. So we are going to make D2 the subject of the formula, which is our D2 there. So we are going to cross multiply. When we do that, we are going to have our P1 times our T2, D2 should be equal to, we have our T1, D1 times our P2 when we cross multiply. Then what we are going to have is that we are going to divide. So to leave D2 alone, we are going to divide P1, T2, like that. Is there any mistake? P1, okay, it's okay. Then we have over, we have our P1, then we have our T2, like that. We are dividing this throughout. So our density number 2 is equal to T1, D1 times our P2 over our P1 times our T2, like that. So the pressure, so D2 is equal to, what is our temperature? So our temperature number 1, which is the one that they have given us, which is equivalent to 450 kelvins. So we are going to replace. So we have our T1, temperature number 1 is our 450 kelvins. So we are going to say 450 kelvins times our density number 1 is equal to 1.41 grams per cubic decimeter times our pressure number 2. So our pressure number 2, it is the STP pressure, which is our 1 atm. Then we divide this by our pressure number 1 is we are dividing pressure number 1 is equal to, we have 2 atm, like that. 2 atm times the temperature number 2 is equal to, remember it is the one that is for STP, which is our 273.15 kelvins. So the density shall be equal to, we have 450 times 1.41 times, we have 1, like that, which is going to give us a 634.5. We divide this, divided by, we have 2 times 273.15. This is going to give us a value of 546.3. We divide this, we are going to have 634 divided by 0.5 divided by our 5 something. That is going to give us a density of 1.16145, like that. So this is the density of the second one, which is our gram per liter, like that. So that is how we answer that one. Let's say we are told to arrange these gases in order of increasing density. So how do we arrange these? So if it is STP, it means to say the density, the volume is the same, which is 22.4 cubic decimeters. And we know that density is equal to grams. It is equal to the mass over the molar mass, mass over the volume. The volume is this one, so the volume is the same. So whatever has got the greatest mass, it means to say it has got the greatest density. So we are going to put first our neon, like that, then we have our Cl2, like that, then we have our F2, like that, and our O2, like that. Then calculate their molar mass. So beginning with our oxygen, it is these 2 times the molar mass of oxygen is 16, which is going to give us a 32. Then we have our fluorine has got the molar mass of 16 times these 2. This will give us a 38. Chlorine has got 2. We have 2 of them times the molar mass of chlorine is 35.45. this is going to give us 70.9. Neon, on the other hand, has got a molar mass of 20.18. So then we have our neon like that, it is 20.18 like that. Then we have our chlorine, it has got a molar mass of 70.9. Then we also have our fluorine, has got a molar mass of 38. Then we have our oxygen, has got the molar mass that is equivalent to a 32 like that. So to find the molar mass, what we are going to do is that the molar mass, so to find the greatest density, we know that density is equal to mass over the volume. The one that has got the greatest mass means to say it has got the greatest density, because let's say if we have 20 over let's say if the volume is the same, if we have 20 over 10, this is just an example, the answer will be 2. So if the mass is 40, maintaining the volume, you will find that as long as the mass is greater, it means to say it will form the greatest density. So now the question was saying that arrange the gases in order of increasing density, meaning to say from the smallest. So among these, the smallest is neon. So we are going to have our neon, then followed by our oxygen, then followed by our fluorine, then followed by our chlorine like that. So the increasing, we are going to add this. So this is how we show chemistry questions. So neon is less than this, oxygen is less than that, like that. So that means to say we have answered that. So here we have a steel tank, has a volume of 438 liters and is filled with 0.885 kg of oxygen. Calculates the pressure of O2 at 21 degrees Celsius. So we are going to say pressure is equal to N. So we have our PV is equal to our nRT. Then we are going to make the pressure the subject of the formula. So our pressure is equal to nRT over the volume. So our pressure is equal to, what is our, we have oxygen. So we can find the number of moles. So number of moles is equal to mass over the molar mass. So it is oxygen, meaning to say the molar mass of oxygen, O2, is equal to, we have a 2 times 16, which is equal to 32. So we are going to have 32. So we have 32. So we are going to say number of moles is equal to our mass, which is equal to 0.885. Now this is the kilogram, so kg. Instead of saying kilogram, where there is kilo, kilo is equal to 10 to the power 3. So we can put where there is kilo, we say 10 to the power 3 grams there. So this K is 10 to the power 3 over the molar mass, which is our 32 grams per mole. So our number of moles for this one, it will be equal to 0.885 times 1000. That is going to give you 885 divided by 32. This is going to give you a value of 27.65625. So we have 27.65625. We divide over the volume. So the volume is equivalent to what is the volume given? 438. So we are going to say 438 liters. So our pressure will come out in atmospheres divided by 438. This is going to give us a value of a 0.0631 atm like that. Let me just confirm doing the recalculation. Oh, we have just put the number of moles there. So pressure is equal to, not like this. So we have pressure should be equal to 27 points. These are the number of moles, 65625, times the universal gas constant, which is 0.08206, times our temperature. So temperature is in 21 degrees. So temperature in degrees Kelvin should be equal to 21 degrees. Remember, you add a 273. So we have just skipped that. So we are going to get a 21 plus 273.15. This is going to give us a value of 294.15 like that. So we divide this or we multiply the value of 294.15 like that, then over our 438 liters. So the pressure should be equal to, we have 27.65625 times our 0.08206 times 294.15, then we divide by our 438. This is going to give us a value of 1.524. So we have our ATM. So that is that for this topic. Thank you very much for watching. Hope you would like, subscribe and share for more. See you in the next tutorial.